Okay, so consider a triangle, and for example, it's centroid x2 over here. Okay, now what am I gonna do? What am I about to do? I am gonna iterate, starting from this point, an alternation of isogonal. So I'm gonna take the isogonal of x2, and I'm gonna get x6, right? And I'm gonna take x6, and instead of computing the isogonal again, which will throw me back to x2, I'm gonna jump to point 2, which is the isotomic of x2, which I believe is x76. Okay, now if I compute the isotomic again, I'm going to be thrown back to 1. I don't want to do that. I want to continue on this path. So now from 2 to 3, I'm going to again apply the isogonal of x76, and that's going to land me somewhere else. I forget what the name of this point is. And then I'm going to alternate. I'm going to get the isotomic and so forth and so on. So I can keep going 5 times, 10 times, 20 times, 50 times. So I have a triangle, I start from x2, and I'm just computing in alternate fashion the isogonal isotomic, isogonal isotomic, and I'm going to get a pattern. Now the main concern of this video is to study if there's anything interesting about this pattern. The first thing we can say is that every point in this succession is a triangle center. So I don't know if this thing is ever going to converge. I don't think it does. So this could potentially be a way of generating an infinite number of triangle centers. Okay, it would be interesting to know which ones of these are currently on ETC. ETC has about 60, 70,000 triangle centers. So maybe some of these are there, right? The isogonal of x2 is x6. The isotomic of x6 is x76. The isogonal of x76 is, I forget now, I wish I could remember it. I think it's x32. It's also on ETC and so forth and so on. So which one of these on this recurrence are currently on ETC? And is this list infinite? Now, second thing I want to show you is what happens to the geometry of this map as I change the geometry of my triangle, which is now slightly obtuse. Let's make it more obtuse, for example. So not much is happening here. What if I go to the 90-degree position? There's nothing of interest going on in this transition. What if I go toward a more isosceles configuration? Now you start seeing a change, right? And you can see very clearly here that there is a geometry to some sort of a bounding curve to this. This is clearly not a conic, so maybe this is a cubic of some kind. Now, as I go through the isosceles configuration, you can see here that everybody's going to go through x2, and all of them are going to fall on the axis of symmetry. But there's still an infinite set of numbers here. Okay, let's keep going. So then you get this reverse situation. And then you have this arch, right? This will continue to go on forever if this number of iterations could be increased to 100. And this is probably going to approach one of the sides. Anyway, so you have this kind of geometry. I don't know if this has been studied before or not, but it's kind of interesting, right? What happens if we start, for example, from a different point? So this is, let's go ahead and go to a different kind of triangle that is scalene. And I just want to move P around without the concern that it be some pre-designated triangle center. So you can see that I can alter the geometry of this sequence of triangle centers by moving P within the interior and indeed in the exterior of the triangle as well, right? So I have this kind of degree of freedom here, 2 degrees of freedom, and I also have the shape of the triangle. So one interesting thing we can see here is that there's a complicated envelope of these points, or a bounding curve. I don't know what to call it, but there's some sort of a bounding curve that is sort of self-intersecting in this case, right? So if you take, for example, I don't know, let's take x11 as a, remember x11 is a Feuerbach point. It lies on the circumcircle of the triangle, on the incircle, right? So if you can imagine in your mind's eye the incircle of this triangle, x11 Feuerbach point is there. Feuerbach point tends to produce this sort of crossover geometry for many triangles. So it's very sensitive here to the geometry of the triangle, right? And it's also going to alter what it is going to do if I, instead of starting with the isogonal, I start with the isotomic. If I start with the isotomic, then you get that same geometry but for different kinds of triangles. So you can see here that I'm getting a complicated self-intersecting deltoidal-like thing. I don't know what to call this, but you can see here that I start, first of all, this thing alternates, right? So this is sort of a pencil of alternating lines. I haven't studied this formally at all. I'm just sort of looking at it with you guys, the viewers, for the first time myself. I noticed that X11 was giving me some interesting phenomena. How about X3, the circumcenter? Is there anything special about it? I couldn't find anything special. It gets a little unstable when triangle transitions into an obtuse triangle, but there's nothing extremely interesting here. How about the in-center? Is there a different curve? It is true that this series that contains the in-center may never produce triangle centers that are spawned off of the X2 series, okay, or the X3 series. Now we know that X3 and X4 are isogonal conjugates, so X3 and X4 are probably spawning off a similar set of triangle centers here. But if you get an unrelated guy like X2 or X1, their series could differ completely, right? So anyway, and I can of course just analyze what happens when P is free. I think I've already done that. But you can see here that you can control this series by just moving P around. All right, thanks for watching.